All right, backing up. What was expected was that the electron can have a continuum of allowed energies. So for example, the electron might be lower energy or it might be higher energy, or it could be any energy in between. But, you know, this is like, for example, the sun. In the sun, the electron can possess any energy. There's going to be different energies because a lot of energy in the sun, so not everything has the exact same energy. And so electrons will have lower energy, maybe infrared, or higher energy, like visible light. No. But we'd see a continuous spectrum. Or a light bulb, you know, with a tungsten. We get a continuous spectrum, you know, when the electron is in a tungsten filament. However, when the electron is confined to an atom, this was expected for atoms too. For electrons confined to an atom. You know, what these two have in common is they have relatively free electrons. That is, the electrons are free to move about as they please. But when an electron is confined to an atom, then the electron's not really free, it's confined to an atom. And when you confine the atom to an electron to an atom, you know, then the electrons cannot possess any energy. This was expected for electrons confined to an atom. But what was observed was called what? It wasn't a continuous spectrum, it was a discrete, or we have another name for it. Starts with an L. Line spectrum. And so what was observed was the line spectrum for discrete, a non-continuous spectrum. This non-continuous spectrum had forbidden energies for the electron. The forbidden energies. And the black lines were the allowed. So most energies were forbidden. Why were most energies forbidden? So this was a kind of mysterious observation. You would expect the electron, even in an atom, you know, so there are two theories that came out of this. The first theory is the Bohr theory. So this led to the Bohr theory. In the Bohr theory, there's the nucleus, let's say of the hydrogen atom, and then the electron can orbit around the nucleus. And so this is the first orbit, which we call the n=1 orbit. And then it can go up to the second orbit. You know, it's possible it can go up to the second orbit, which would be the n=2 orbit. So it can go up or down, like the floors of a building. And so if the electron goes up, it goes higher in energy, it absorbs some energy. If the electron goes down, it goes lower in energy and it releases some energy. Or it could go up to the third orbit, n=3, all the way out to the n=infinity orbit. The n=infinity orbit is going to be an infinite amount of distance away. And so we have orbits. And so what Bohr said was that, why can't it be between the orbits? So for example, n equals 1.1, it just goes a little faster, orbits a little bit farther, a little bit faster, a little bit faster, a little bit faster. Why can't it go to any speed or any orbit it wants? And Bohr it basically said it just can't. Now, the n equals infinity orbit is basically what we call an ionized electron. If the electron gets promoted all the way up to n equals infinity, then the atom's lost the electron, and therefore we create the ion. For example, hydrogen, if hydrogen's electron goes all the way to n equals infinity here, then the electron's gone. It's the hydrogen ion or the proton that we're left with. Now, the n equals infinity orbit's very far away. However, the energy is not. So it's not infinite energy. It doesn't take infinite energy to get to n equals infinity because the orbits diverge. And so we see these diverge. That is, what happens with the orbits is they get further and further apart as we go higher and higher. However, the energies of these orbits actually converge. And so the n equals infinity is not way up there, infinite energy. It's actually not that far away. The n equals infinity orbits, now we have an infinite number of lines here, but initially it spreads out and then it just gets tighter and tighter here. So what happens is the biggest gaps are at the beginning. So this is n equals 1 here, n equals 2, n equals 3. And so what happens with the energies is the energies converge, whereas the orbits diverge. They converge, actually, the energy here, as we call it, 0. It's an arbitrary 0, relative 0. And then the energy down here is, we call it minus r sub h, negative energy there. But this one, you don't have to know this. And so this worked at getting the patterns. We could see the patterns of the lines based on this. And the patterns of the line that Bohr said is this. Bohr said if there's an electron on the 3rd floor and it drops to the 2nd floor, we get a red line in the spectrum. If there's an electron on the 4th floor and drops down, we get the green line. And then if there's an electron on the 5th floor and it drops down, we get a blue line. And then what do you think the violet line's from? The violet line would just be from the next floor. The violet, I'll just try to do it like that. We get the violet line. Blue line. Blue line is going to have longer wavelength. Green line will have an even longer wavelength, lower energy. The red line will have the longest wavelength. If we drop from the next floor, then we get UV. This one will emit UV. The same thing from the 2nd floor to the 1st floor is UV also. But from, let's say, the 4th floor to the 2nd floor is IR. Right? And so we get a whole bunch of lines corresponding to these electrons. The electrons are going to populate the higher energy states just due to collisions and energy. So electrons can jump up floors, but then when they drop down, they can emit the energy. And so why is it like this? And so that was one of the things. And so the Bohr theory proved to be wrong. Bohr theory, the end result is Bohr theory is wrong. Why is the Bohr theory wrong? Not entirely wrong, but wrong. We don't use Bohr theory anymore. We don't use Bohr theory because, well, these Bohr theory is orbits. They don't go in orbits. You know, electrons don't orbit. The Bohr theory is wrong because it could not predict the spectrum for other elements, for other atoms. A theory's got to be able to predict. Could not predict. Spectrum. We call it spectrum. Is the this is the spectrum, continuous spectrum, line spectrum. Could not predict the spectrum of other elements. So then it was abandoned. Bohr theory is wrong. And it was replaced with the Bohr model, or Bohr theory evolved into the quantum mechanical model. Why is it that when the electron is confined, when the electron is confined to an atom, we only see certain energies allowed? And why that is because, for example, if you hit a gong, can you get any tone out of the, or a drum? If you hit a drum, can you get any, big drum, small drum? Do they make the same sound? No, that means there are some drums you can't get like the same sound from a big drum as you can from a small drum, and vice versa. And it doesn't matter what you do, you just can't get it because those are not allowed. Those sounds are not allowed. And so there's sounds that are allowed and sounds that are forbidden. Well, when we beat on a drum, that's what we call a standing wave, and so it depends on how big the cage is. If the cage is big, then what's allowed is different than if the cage is small. Right? This is like an electron. Electron is, electron has a wave-particle duality. And so what Bohr didn't account for is Bohr didn't account for the wave parts. And so when an electron is confined to an atom, it's like this. This metal plate can only have certain sounds that are allowed. Do you want to hear what sounds are allowed in this metal plate? Actually, you already heard it, but basically, let's see. So if you listen, right there, okay, right there, that's allowed, but any sound before that was forbidden. And so this metal plate is only going to vibrate at a certain if this is forbidden, this metal plate can't make this sound. Okay, this is allowed here. Do you see that? And so what they're doing is they're exposing this metal plate. This metal plate will, if you beat on this metal plate, it'll only make these sounds. Like it'll have a fundamental sound and then overtone sounds as you go up higher and higher in energy. And so we see that things, when an electron is confined to an atom, things naturally become quantized because the electron is like caged in a container. It depends on how big that container is. It's like a fish. Can a fish move at any speed it wants? Well, sure, the fish should be able to move at any speed it wants, right? At any speed it wants in the open ocean. If the fish is free, it could move up to any speed it wants as long as it's within its range of speeds. But what happens if you confine the fish to a small box? If you confine the fish to a small box, maybe you can get one kick out of there versus the open ocean. The open ocean, the fish can move slow or fast, but here, let's say the fish gets one kick in there. That's one speed. Or the fish can get 2 kicks in there, or whatever you call that, you know? It's another speed. You know, and so they're just like this, you know, the fish is going to be confined to a small container. If the fish is confined to a small container, then its speeds are going to be quantized depending on how it can move. It's not a perfect analogy, but do you see what I'm saying? Versus if the fish were, it's like the whales. You go to see the whales out like wherever SeaWorld or something. They're confined to that. Can a whale move its maximum speed in a tiny box like that? No. Can it move any speed it wants? No. It's confined. And so electrons are kind of the same thing. It's confined. It's not free. And so this is why, you know, the solar spectrum, we get the continuous, but when the electron is an atom, it's not. And so what that comes up to is that the electrons occupy strange shaped things like this. These are called wave functions. And so we come up with a new model, which is quantum mechanics. In quantum mechanics, we get rid of the idea of orbits. Orbits are wrong. And we replace that with something that sounds very similar. We replace it with something called an orbital. And the orbitals are going to have different shapes, like you see, the standing waves there. The simplest orbital is going to have a spherical shape. This is an S-type orbital, which is spherical. And then some of these orbitals can have a dumbbell shape like this. This is called a P orbital. And it's like this figure 8 type shape. And then we have these orbitals that look like this. They're like cloverleaf. This is called a D type. And they get more complex as we go along. Let's take a look at some orbital shapes. So here we see the S orbital. So electron, it looks not like this is, rather than an orbit, it looks like this. This is a P. This is a D. The Ds are these cloverleaf type shapes, and they can be more complex. Like this one looks like a P orbital with a hula hoop around it here. And then we get to the F orbitals. You see, each of these round things is called a lobe. These are F's. This is probably not the greatest image of that. It's a little easier to see. And then they get more and more complex. They'll have more and more lobes, just like the pattern on the metal plate. These patterns can get quite complex. Now, what does the orbital represent? So that's what we want to know. You know, what does this represent? Well, the orbital is the allowed energy for the electron. And it has two basic things that we get from it. One is the energy. And two is from the Heisenberg uncertainty principle. You know the Heisenberg uncertainty principle? What's that? The Heisenberg uncertainty principle means that if we pinpoint energy, if energy is defined, then position is poorly defined. What I mean by poorly defined is it's not, you can't be anywhere. There is some certain probabilities. The shape of the orbitals gives the probability defining shape of orbital gives probability of finding an electron. So normally there's like 95% probability of finding an electron. And so what we have here is, let's say, if the electron for the hydrogen atom can be in different orbitals. So the H atom, the lowest energy orbital is like this. This is 1s. N equals 1, and it's an S-type orbital. It looks like this. So here's the nucleus. Now, when we think about probability, this is like a bird. You know, if you think about a bird, let's say this is the nest of the bird. Okay, can you predict, or can you tell me in, let's say, 30 seconds where that bird's going to be? Precisely? Can you tell me in 30 seconds that bird will be here? And then in the next, let's say 30 seconds later, can you tell me where that bird's going to be exactly? No. And so the position of the bird, is it well defined? Is it precisely defined? Is it pinpointed? Well, for example, we can pinpoint the position. The bird's here. But can you tell me where that bird's going to go next? You know, how much energy does that bird have? We don't know. And so what we do is we do this. Okay, the bird's here, then the bird's here, then the bird's here, then the bird's here. And so what we do is we know, well, the bird doesn't have a tremendous amount of energy, so most of the time it's close by the nest. But sometimes it gets further and further from the nest. And so we look at the position of the bird and plot it out as an area chart like this. And then we see, okay, since this bird doesn't have too much energy, you know, its probability of being way out here is kind of low. And so if the bird doesn't have a lot of energy, its probability of being like 30 miles away is minimal. But there is a probability that the bird might be 30 miles away. And so what we're going to do is then we're going to map this out. We're going to say that there's a 95% probability of finding the bird within this boundary. That's what this is. What that sphere represents, the blue sphere up there represents, is this 95% probability of finding an electron in that sphere, and a 5% probability of finding it outside that sphere. Now, what happens if the bird has higher energy? What happens if the bird has higher energy is this. Let's put the nest here. What happens is that the bird can be farther out from the nest. And so what we're going to see is we're going to see the probability distribution expand. You know, obviously it can be close to the nest, but the probability of finding it outside or further outside the nest is higher. And so if the bird has higher energy, then we got to expand this. So this would be 2x. And so normally the bird is down here. We'll put the electron like this. Normally the electron is down here. This is called the ground state. If this electron gets excited, then it can get promoted to what we call an excited state. This would be an excited state here. Excited state. And so it's just a higher energy state. Is it going to stay in the excited state forever? No, it's going to, eventually it's going to drop back down to the ground state. And so what we have here is a similar type situation. You know, rather than the electron going to higher energy orbits, as in the Bohr model, the electron goes to higher energy orbitals in the quantum mechanical model. Now, what are all the orbitals? It turns out there are a lot of orbitals, actually. This might be. There's some rules for this. You know. based on quantum mechanics. It turns out there are other orbitals. This is called a transition. There are rules for transitions. I just violated one of them with the transition. We don't have to worry about the rules. But there are some allowed transitions and some forbidden transitions. And so over here we have our 2p, and there are three of them. There's the px, the py, and the pz. So here we would have the 2px, the 2py, and the 2pz. These are all the same energy. They just differ in their orientation. So for example, the x is oriented along the x-axis here, the x-axis. The y is oriented along the y-axis here. And the z is oriented along the z-axis here. The z will have vertically. But they're all the same looking. They're big. I'm not drawing these that big. But this is, this is confining the electron within this boundary here, 95%. For the hydrogen atom. For the so one thing we want to know is, where do these orbitals come from? Why do we get these bizarre shapes, and how do we get the energies? Do you know where the orbitals come from? They come from quantum mechanics. The theory. So let's just say quantum theory. The orbitals come from quantum theory, and there's an equation, a mathematical equation in quantum theory. Do you know what the name of that equation is? It starts with an S. Schrodinger equation. We are not going to get into the math of the Schrodinger equation, but we know that the orbitals are the solution to the Schrodinger equation. Each atom has an infinite number of solutions. Even though there's an infinite number of solutions, there's also an infinite number of forbidden solutions. And so, for example, this n can be 1, n can be 2, but n can't be 1.1 or 1.01 or 1.11. They can't be anywhere between, so those are forbidden. So we could say, and an infinite number of forbidden. So each of, let me say allowed here, allowed solutions, and an infinite number of forbidden solutions. So if we take the hydrogen atom, there's one ground state, but there's like an infinite number of excited states. And so how can we figure out what those infinite number is? It seems like impossible, right? Impossible. But it's not impossible because the solutions, the orbitals, follow mathematical pattern. Orbitals of the allowed energies and the positions of the electrons follow a mathematical pattern. So let's take a look at the typical pattern, typical atom here, typical pattern. It's a number pattern. And so let me just show you the number pattern first. We call this one the 1, 0, 0. It's the first one. And then the next one is called a 2, 0, 0. And then this all goes all the way up to infinity. Infinity here. 0, 0. And so what comes after the 2, 0, 0? After the 2, 0, 0, you expect a, if you think. Actually, this should be the biggest gap here. What did you say? 3, 0, 0. After the 3, 0, 0, what do you think? You think comes next? The 4, 0, 0. After the 4, 0, 0 would be the 5, 0, 0. And so we give these orbitals names. So for example, the 1, 0, 0 is called the 1s. The 2, 0, 0 is called the 2s, 3s, 4s, all the way to the infinity s orbital. But along the way, things get a little bit complicated because between the 2, 0, 0 and the 3, 0, 0, we see 3 lines. I don't want to draw them in here because it'll get all messed up. But just slightly above the 2, 0, 0 in terms of energy, we have 3 additional orbitals. Each of these represents, each line represents one orbital. And so the 1s orbital, the 2s orbital, and then we're going to have this. This is going to be the 2, 1, negative 1, 2, 1, 0, 2, 1, 1. These are called the 2p orbitals, and there are 3 of them. The px, the py, and the pz. So, for example, we could call this the 2px, 2py, 2pz. Well, the third number here, the negative 1, 0, that has a bearing on this. And then after the 3, 0, 0, just slightly above the 3, 0, 0, we have the same thing happen. We get the 3, 1, negative 1, 3, 1, 0, and the 3, 1, 1. These are called the 2p. You know what we call these? The 3p. The 3p look like the 2p, but they're a lot bigger. More energy. You know, the more energy, the bigger the probability these should be. And then after the 4, 0, 0, we have this one. The next one that comes up here. I'm going to write it over here because there are 5 lines, and these lines are all the same height, the same energy. These ones are called the 3, 2, minus 2, 3, 2, minus 1, 3, 2, 3, 2, 0, 3, 2, 1, and 3, 2, 2. Do you see kind of a pattern with the numbers? These ones are called the 3D orbitals, and there are 5 of them. we have little designations for those 5. So for example, we have the dx squared, 3dx squared minus y squared, which looks like this, the 3dxy, the 3dyz, the 3dxz, and the 3dz squared. That's what they look like. Those are the orbitals, and they're all the same energy. Those 5 individual orbitals have the same energy. And then after that comes the 4, 1, negative 1, 4, 1, 0, and 4, 1, 1. These are the 4p orbitals. And so then it goes on, etc. There are a whole bunch all the way. It'll converge. The orbitals get tighter and tighter, and they'll converge at infinity. There. Now, what these 3 numbers are, we have letter designations for these. And so the 3 numbers are N, L, M. M is the principal energy level. And so the higher the N, the higher the energy is. L is the angular momentum. Quantum number. Angular momentum, this tells us 2 things. One, it tells us the shape. So this is why I split them off. All these have the same L. What's the L? Is 0. And all of these are going to have the same shape. What's the shape? Spherical. And then over here, what's the second number? The second number is L. All these have the same L. What's the L? 1. They all have the same shape. And so over here, we'll write L equals 0. Over here, I'm going to write L equals 1. Over here, what's L equal to? L equals 2. It's the second number. The first number is N3. Second number is L, which is 2. And so this is L equals 2 here. M is going to tell us the number and orientation. The number of orbitals is a little bit tricky. The number of orbitals comes from the allowed M values. Number of orbitals comes from the allowed M values, from the number of allowed M values. So for example, if L equals 0, M only has 1 allowed value, 0. If L equals 1, then M has 3 allowed values, -1, 0, and 1. So here you can see when L equals 1, we have 3 allowed M values, -1, 0, and 1. Those give us, those are numerical codes for the PX, PY, and PZ. When L equals 2, then M can have -2, -1, 0, 1, and 2. When L equals 2, there are 5 allowed M values, -2, -1, 0, 1, and 2. Those correspond to these here. The code number for those. And so there are 5 allowed orbitals here. Each of those M values has a different orientation. There are 3 allowed M values here. Each of those, there's only 1 allowed here. There's only 1 orientation. So this is the orbital energy level diagram, all this. So let's say an electron were down here. Normally it's in the 1s orbital. So normally an electron is here. And what does the sphere represent again? And the sphere represents well, orbitals represent two things. They represent the
probability of the electron.
Yeah, the probability, so that sphere is a boundary. It's not a hard wall. That sphere is just an invisible boundary that says that the electron should be found within that boundary. It's like a wall. It's like this sink, you look at the splatter pattern in the sink. Well, it depends on how much energy water is coming out of the faucet. And you look at that splatter pattern and then make an invisible circle. That invisible circle says 95% of the drops of water will be contained in there, and then 5% might be outside. Then you crank up the pressure, and then you're going to get a bigger splatter pattern. And so basically this represents the probability of finding an electron within 95% within this boundary. There's 5% it's outside. It's like the bird. There's a 95% probability of finding the bird inside there, 5% outside, but it's not a real wall. The bird can travel. You're just looking at. Now we compare that, that's lower energy. If we go to higher energy, that boundary grows a lot bigger. And so in terms of the orbitals here, the 1s orbital is going to be quite a bit smaller. 2s is bigger, 3s is bigger, 4s is bigger as energy goes up. And the same thing, the 2p's are these dumbbells. So the 2p's are a certain size, the 3p's are going to be a lot bigger, 4p's are going to be a lot bigger, as well as the d's. All right, so let's look at the number patterns here. There are more number patterns than we can see, but I'm not going to go through all the number patterns like this. But, well, n can be 1, 2, ... What's the maximum n value? Infinity. So there's a number infinite allowed, but n cannot be 0. N cannot be other things. L is going to be all values from 0, 1, ... to a max of n minus 1. So we can see that here. What is n here? N is 1, it's the first number. Okay, if n equals 1, what is my allowed L value? My allowed L value is n minus 1. 0 up to a max of n minus 1. Well, if n is 1, then 1 minus 1 is 0. And so I only have one L value allowed. That's 0. And then m is going to have all values from minus L to minus L plus 1 to ... through 0, ... through L minus 1 to plus L. And so here, if L is equals 0, then we're allowed all values from minus 0 to plus 0. Well, all values from minus 0 to plus 0 is just 0. Over here, if L equals 1, then we're allowed all values from minus 1 to plus 1. Well, what are all values from minus 1 to plus 1? It would be minus 1, 0, and plus 1. 1.1 is forbidden. 0.9 is forbidden. It has to be an integer. If L equals 2, what are my allowed m values? Well, all values from minus 2 to plus 2. So minus 2, minus 1, 0, 1, 2. And so this is how we're going to build up this this chart. When n equals 2, then what are my allowed L values? When n equals 2, what are my allowed L values? We start off at 0 is allowed. Is 1 allowed? Is 2 allowed? No. If n equals 2, L equals 2 is forbidden. And so it stops here. There's no L equals 2. And so we stop. And so what we call these is we call these subshells or sublevels. So we can get that from this other pattern. There are n sublevels for each n. So if n equals 1, how many sublevels do we have? We just have 1, the 1s. When n equals 2, how many sublevels do we have? Well, we have 2. We have the 2s and the 2p sublevels. When n equals 3, how many sublevels do we have? We have 3 sublevels. The 3s, the 3p, and the 3d. 3 sublevels. Those 3 sublevels come from the allowed L values. When n equals 3, the allowed L values are 0. Well, that's the S sublevel. L equals 1, that's the P sublevel. And L equals 2. L equals 2 is called the D sublevel. And then that's it, that's the max we're allowed. So when n equals, let's go to n equals 5. When n equals 5, how many sublevels are there? There are 5 sublevels. What are they? Well, they're the L values. So if n equals 5, then I'm allowed L equals 0. Is that allowed? L equals 1. Is that allowed? So 5, 0, that's called 5s. 5, 1, is that allowed? Yes, that's called 5p. 5, 2, is that allowed? Yes, that's called 5d. L equals 3, is that allowed? Yes, we call that, you know what we call it? We call it 5f, the 3f. L equals 4, is that allowed? Yes. Yeah, we call that 5g. L equals 5, is that allowed? No, that's forbidden. Why is it forbidden? Because if we try to plug in L equals 5, when n equals 5, into the Schrodinger equation, do you know what happens? It comes out false. So it's like this. It's like here. 2x is equal to 6. This is how the Schrodinger equation works. If I try to plug in, well, I'm going to try to plug in 9. Is 9 an allowed value for x? No, that's a forbidden value. And so 9 is not allowed. There's only one allowed value for x. What is it? 2x equals 6. The allowed value for x in this equation would be 3. Everything else is forbidden. Well, this is exactly what we're doing with all these numbers. With all these numbers is you plug those into the Schrodinger equation, and it's either going to give you an allowed answer or a forbidden answer. And so this is how we generate things. And so when we go to n equals 100, how many sublevels are there? 99. What are they? 100s, the 100p, the 100d, the 100f, the 100g. Pretty soon you get tired of doing these letters. And so pretty soon you get tired of doing those letters, so what you do is you just do the numbers. So what's allowed? Well, what's allowed is the 100, 0. That would be 100. What's the next one that's allowed? The next one that's allowed would be the 101, then 102. Does that make sense? No? And so we can generate this by using these patterns. And so let's take a look.
So these orbitals, these levels are the levels of increasing energy for the electron?
Yeah, they would have different shapes. Let me show you. Actually, maybe what I'll do is we'll just show you some off the internet. What are these diagrams called here with the energy going up? What is it called?
Orbital energy flux
Orbital.
diagram.
Okay, so let's search that. Orbital energy level diagram. So, let's see. Here's one. So this is it here. These are the allowed energies for the electron. So the electron can be occupying any of these orbitals, which would be allowed. There's a certain pattern to be here, and that is this. When we look at n, you know, n equals 1 is going to be lower in energy than n equals 2. It's going to be higher in energy than n equals 3. So this would be the energy. And so the energy increases as we go up this way in n. L will have a little bit of an impact, you know, with the energy. So if I compare it, let's say this is L equals 0, this is L equals 1. So, you know, L equals 0 is slightly lower in energy than L equals 1. In other words, a 2s orbital is a little lower in energy than 2p. And so as we increase L, look at what happens. 3s and then 3p. Well, we're going from L equals 0 to L equals 1. And then from 3p to 3d, we're going from L equals 1 to L equals 2. And so L will have an impact, but the biggest impact in energy will be N. And so as L increases, let's say 0, 1, done the same, 2, etc., we see a more minor increase in energy. Here we're going to see a more significant increase in energy. See a more minor increase in energy for a given N. So this is what gives this weird pattern here. Now that weird pattern, there's a pattern to that as well. So let's look at the energies in order. The lowest energy is 1s. And then up in energy would be the 2s. And then just slightly higher in energy than 2s will be the 2p's. And then we'll jump up to the 3s. And so we'll go 1s, 2s, 2p, and then 3s, and then 3p. But something weird happens here. And what's weird is we expect the next one to be 3D, but the next higher one is 4s, and then 3D, and then 4p. And so there is a pattern to that as well. And so the pattern to that is it goes like this: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. And so we add one as we go along. And so the energies are going to go like this. The 1s will be the lowest, and then the 2s, and then the 2p, 3s, and then the 3p, 4s, 3d, 4p, 5s. 5s here. Okay. So these are split up into L's, N and L's. You know, L equals 0 here, L equals 1 here, L equals 2 here, L equals 3 here. So we can add an L to each subsequent line. All right, let's stop here, take a break, and then